Hi, I'm Mike Abbott, and for my Capstone project, I developed a system for automatically calibrating pressure advance on 3D printers using laser triangulation. Here's a picture of the system installed on my 3D printer. So what is pressure advance anyways? First, let's talk about what happens on a printer that doesn't have pressure advance enabled. As the 3D printer operates, the tool head moves around the print. The printer automatically adjusts the amount of filament that's pushed out as the velocity of the tool head changes. Whenever the tool head approaches a corner, it has to slow down a lot. When this occurs, the extruder pushes out less filament. However, there is a small amount of pressure that's built up inside the hot end. Even though the printer isn't pushing out filament, a little bit continues to leak out. And when the printer begins moving again, there is a small delay before filament continues to exit the nozzle. This is because pressure has to build up again before plastic is pushed out. On printers with high acceleration settings, this can lead to issues like bulging on sharp corners, as shown here. Properly tuning pressure advance can prevent these defects. Pressure advance works by preemptively pulling back on the filament when the tool head is coming to a stop and pushing a little bit extra when the tool head begins speeding up. Pressure advance can be tuned in a variety of ways, though for this project, we'll just talk about the lines method. If you print a straight line that has a period of slow motion, then fast motion, then slow motion, you will see defects at the area where the tool head speed changes. Even though the extruder is pushing out the correct volume of filament during the entire motion, the lag caused by pressure building up and releasing causes gaps and bulges. The pressure advance value determines how much the printer compensates for this issue. The correct value can vary from printer to printer, and even things like changing filament or printing temperature can impact the appropriate setting. The lines method of pressure advance calibration works by printing the pattern we just showed, but with a different pressure advance value for each line. By looking at the printed pattern, we can estimate the appropriate pressure advance value by picking the line that looks the most consistent all the way across. For the pattern shown here, I think that this line looks the best. This pattern has 10 lines in total, and the values tested range from 0 to 0.06. Since this is line number 5, the value used to print this line was 0.03. If we tell the printer to use this value and then reprint the pattern, this time around it will look like this. Pretty neat, huh? But here's the problem. What if I change the material I'm printing with? Then I have to do this calibration process again. Or if I change the temperature that I'm printing at. Even different colors of the same filament work best with different values. And who wants to recalibrate every time they change anything? Calibration takes time, and so a lot of people, myself included, just pick a value that's good enough and leave it. But what if we could do this automatically instead? Over the last several months, I've been developing a system that's capable of doing just that. I call the system Rubedo, and it uses an off-the-shelf line laser and USB camera to generate a 3D scan of the printed pattern. Here's a closer photo of Rubedo attached to my printer. The entire system consists of just two parts. On the left is a USB nozzle camera from 3DO, and on the right is an adjustable focus line laser I picked up from Amazon. Rubedo uses a process called laser triangulation. This works by analyzing the shape of a line laser as it hits a surface. By shining the laser from an angle, the beam can show us the height of the object it strikes. For example, look at these two photos. The image on the left shows the line laser intersecting an area where the printed lines are very thin. The U-shape where the laser touches the line is very small. On the other hand, the lines on the right have large blobs of plastic. The laser's shape changes much more dramatically here. We can use this behavior to our advantage. Since the shape of the laser is relatively easy for a computer to figure out, if we take a video while moving the laser across the pattern, we can do a bit of math to figure out the shape of the line. Let's watch a video of that process. That was a little quick. Let's watch it one more time, but slow it down a bit. Notice how the laser's shape changes as it moves across the line. Once Rubedo has recorded a video for each line in the calibration pattern, it needs to figure out which one is the best. It does this by analyzing each frame in the video and saving the shape of the laser. Rubedo starts by getting rid of most of the image. There's only a very small section that we care about. Since we only care about the laser right around the printed line, most of the image would just confuse the program. After that, the system gets rid of all the pixels that aren't red. This makes it easier for the software to know what is and isn't part of the laser beam. It also converts the image to black and white, since from here on out we only care about how bright the image is. Finally, the system performs a blur. This makes it really easy for the computer to find the middle of the laser beam, since the pixels in the middle are now the brightest. Once we know which pixels are the brightest, we can graph them. This image is what the system generated for the image we were just looking at. Pretty wild that we can get such a crisp looking line out of an image that's only 60 pixels tall. If we repeat this process for the entire video, we get a 3D model of the entire printed line. These pictures here show 3 different lines from a calibration pattern. The 2 graphs on top are from the same line. Look at how easy it is to see the blobs and gaps in the lines on the bottom. The line on the left had a pressure advance value that was too low, whereas the line on the right had a pressure advance value that was too high. Rubedo analyzes the data in these figures to give a score to each printed line. It does this by calculating the standard deviation for each row in the graph. Then it takes the values for each row and adds them together. This number tells us about the imperfections in each line. The larger the number, the worse the line is. By generating a score for each line, we can automatically pick the pressure advance value that gives the smoothest line. Rubedo can see really small details too. Here's a picture of a line that has a wisp of filament trailing off to the side. When Rubedo scanned this line, it had no problem seeing it, even though it's less than 0.1 millimeters wide. I've been working on Rubedo since the end of last year. When I first started the project, I bought a cheap USB endoscope and the cheapest line laser I could find on AliExpress. You can see them in this picture. Unfortunately, the endoscope had to be too far away from the build plate to get a good picture. It would probably be possible to get working with the system if you opened it up and manually adjusted the focus, but that was more than I wanted to deal with. In addition, the line laser was very difficult to work with. The focus couldn't be adjusted at all, and so the beam was very thick. I originally tried to solve this problem using a 3D printed slit mask, but even though the beam was much thinner, the laser was also a lot dimmer. This made it a lot harder for Rubedo to find the laser beam. Thankfully, I was able to find a laser with an adjustable focus, which resulted in a much tighter beam. You can see the new laser on the left and the old laser on the right. One of the biggest improvements came from obtaining a black PEI print bed. During my early tests, I noticed that the laser had a tendency to diffuse through the PEI. When I shined the laser on my textured bed, it was even worse. The laser just scattered everywhere. I wanted to find a print surface that made it easier for the camera to see the laser. Thankfully, Fabreeko sent me 2 Honey Badger print beds to try out with the system, one textured and one P-series bed. This made a huge difference. You can see in this image how crisp the laser looks on the P-series bed, and even the textured bed still has a pretty clean beam. Once I had several print beds to test with, I wanted to prove which one worked best, and also try Rubedo with both black and white filament. I decided to print the calibration pattern 27 times on each print bed, with both colors, with and without lights turned on in the room. This is what it looked like with all 27 patterns printed. In total, the system scanned over 3,000 lines. I gathered the scores from every line and generated these charts. Each row shows the results for a different print bed. The columns on the left used black filament, and the columns on the right used white filament. Even without looking at the R-squared values, it's obvious that the results from the P-series bed have very little spread. The textured and regular PEI beds performed about the same, although there are more outliers on the normal PEI. Generally speaking, the system performs better with the lights off. This isn't a huge surprise, as ambient light can drown out the laser beam. This effect could be minimized by using tinted acrylic panels or a brighter beam. This also may be part of the reason why the Bambu Labs X1 Carbon enclosure blocks out so much light and uses a tinted glass panel on the door. Moving on, this figure shows how often a particular pressure advance value is selected. Once again, the P-Series build plate was the biggest factor in getting consistent results. The other two build plates were right most of the time, but there is still more spread. This isn't totally unreasonable, as the range of values tested was fairly small, and some of the lines really do look fairly close. For the most part, white filament seems to work slightly better than black filament, though with the P-Series build plate the effect isn't nearly as noticeable. I do believe that with a little bit more testing, the results on the PEI and textured beds could be improved. There are still a lot of things I wanted to try out, and I just didn't have enough time during my first pass of this. In addition, it should be possible to print a second copy of the pattern and average the results to decrease noise in the data. Honestly, there's still a lot of low-hanging fruit here, and I anticipate that the system will continue to improve with more development. There's also some minor stuff like scanning more than one line at a time and integrating this with Clipper that will improve the user experience, but that can all be added later down the line. Now, with all of that being said, let's take a look at the system in action. This is the first time I've shown the entire process start to finish in public, so I'm very excited. The printer will start by printing and scanning the calibration pattern. Once it has picked a pressure advance value, I've configured the system to print some extra patterns to show how well the system worked. The printer will bring the hot end back up to temperature and print a pattern with pressure advance turned off. Then, it will print one last pattern using the pressure advance value it picked from the calibration pattern. Once the video is over, I'll show a better photo of all three patterns and discuss the scores. The system did a great job. I think in this instance, it may have picked a value that was slightly too low, but as you saw in the earlier pictures, that still happens sometimes. In any case, the calibrated pattern looks significantly better than the control. Only minimal deformation at the spots where the velocity changes, and there are no visible gaps. Looking at the results printed by Rubedo, the calibrated pattern has a significantly lower deviation than the control pattern. I think it's really awesome to see everything all working together after I spent so much time on this project. I've got a link to the repository in the description. The code is still a little messy, and you'll still need to edit some parameters in the code and run the script manually, but I'm excited for this to get out in the wild, and I think that there will be lots of exciting developments in the future. Thanks again to 3DO for providing the nozzle camera, and Fabreeko for providing the build plates. The project wouldn't have been able to achieve such awesome results without the awesome hardware to go with it. I should note that the nozzle camera I used was the 1080p version, which is no longer available. However, 3DO has a 4K version of the camera with an even better looking image, and it's capable of 60 FPS at 1080p, so it would probably work even better. Also, thank you to Oren from the Alchemical 3D project. He's offered help every step of the way, and I've been working closely with the other engineers there to help make sure that we can integrate Rubedo into the printer we're currently developing. If you want to follow our progress, be sure to check out the link to the Discord in the description. And last but not least, thank you to all the awesome open source projects that have made this possible. Clipper and the Voron community have done some amazing work and truly pushed the boundaries of what's possible for open source 3D printing. Thanks for watching.